So, torque, or the turning effect. Torque is the turning effect or movement of a force, and the equation is as shown, which is torque equals force times moment arm, and the moment arm can either be the load or the effort arm. In the example shown as the bicep curl, the load arm is the turquoise line and the effort arm is the yellow line. Which is the moment arm in this example, and it's 0.2 meters. And then the force acting down upon that, which is the weight, and the weight of the man's forearm is 30 newtons. Therefore, using the equation, the torque is 6 newton meters. And that's then the turning force which is needed to move the dumbbell. It can be manipulated as and when the F arm is at its shortest, which will be when the dumbbell is at 90 degrees, as it has the largest moment arm, which means that the most force is then required to be able to lift the weight. So that will be when the bicep curl is at its hardest to be able for the athlete to do. So I need to put in more force when it's at 90 degrees. Moving on to my gymnastics analysis, we have the planes and axes. The example here of a gymnastics person doing a cartwheel, they're in the frontal plane, which splits the body right between the middle. It splits into a front and a back, which then allows for abduction and adduction. And then the axis, which is the red dot, which is the point in which movement occurs, would be the anterior posterior axis. And then in the second example of the gymnast doing a spin, they're in the transverse plane, which splits the body into a top and a bottom and allows for flexion and extension. Allows for rotation, which is what she's doing. And then that's in the longitudinal axis, which is an axis which goes through the head down all the way to the bottom, which is the point at which the athlete will rotate off. And then the last example of the athlete running towards their gymnastics routine is in the sagittal plane, which allows for flexion and extension, and splits the body into a left and right hand side. And then the axis is the mediolateral axis, which would go through sideways from points of movement, such as the knees, ankles, or hips in this example. And then moving on to acceleration, deceleration, and velocity. So the angular velocity in this example of the uneven bars, where the athlete is rotating around the bar in an anti-clockwise direction, the equation for angular velocity is angular displacement over time taken. So in this example, she would rotate 180 degrees or 3.14 rads in 1.2 seconds, which would therefore give an angular velocity of 2.66 radians per second. And then for angular acceleration and deceleration, the equation is the change in angular velocity over the change in time, and the angular acceleration, as we know, the change of velocity is from 0 to 2.66, so that's the angular velocity. And then the change in time is 0 to 1.2 seconds, therefore meaning that the angular acceleration is 2.21 radians per second squared, which would therefore be her acceleration from point A, where she starts, and point B, which is where she would end at the end of the arrow. And this would be the same for angular deceleration. Then moving on to center of mass and stability. The center of mass is an imaginary point at which the weight of an object can be considered to act and be equal on either side. And athletes can manipulate their center of mass to be able to then start movement is the example of the front flip. The athlete would have to lean forward and almost fall over to move their center of mass in front of them, which would then allow them to do their movement and jump off the ground and rotate. But to be able to do that, they have to manipulate their center of mass so that it moves forward, so they're then able to do that movement. And then with stability in this other example on the beam, they need to make sure they're keeping their center of mass directly above the point of contact to then remain stable. As you can see with the arrow, the point of contact is their leg, which is directly, and then their center of mass is directly above on the beam to make sure that they then stay on the beam while they're doing their routine. And then moving on to the lever systems. The first class lever system is shown here in the forward roll with the use of the neck as a lever system, in which the load is the head and the neck is the fulcrum, which is in the middle for the first class lever, and then the effort would be the neck muscles, which are just behind, which would then be able to then move the head up and down when doing this action. The second class lever, as shown, the fulcrum is down at the foot, at the ankle, where the gymnast is moving off and sprinting. And then the load is in the middle. It's quite hard to show here as the yellow arrow, but it is her body weight. And then the effort would then be her leg muscles pushing herself off the ground and then moving forwards into the sprint and then into the routine. And the second class lever is mechanically advantaged and mechanically efficient as the effort arm is bigger than the load arm, which therefore means it's mechanically advantaged as a lever, as the effort arm is always longer than the load arm, and the second class levers are made for force generation and strength. And then moving on to the third class lever, the fulcrum, as you can see, is the shoulder, with the load being the body weight and the effort being the bicep muscle. The third class lever is always mechanically inefficient and can't be mechanically advantaged, as the load arm is always bigger than the effort arm, which means more force is required to be able to then move the lever, as it would be in this example where the bicep muscle would be having to do a lot of work to be able to hold up the full weight of the body. And these levers are mainly designed for strength. No, they're not designed for strength, they're more designed for speed and range of movement, and the other two are designed for strength. And then moving on to angular momentum. The equation for angular momentum is the moment of inertia times angular velocity, and to find out the moment of inertia you need to do the sum of mass times the distribution of mass. So in this example, the gymnast is flipping over and the radius from the axis, shown as the red line, is 0.74 meters, and then the mass of the gymnast is 47 kilograms and their angular velocity is 6 radians, which therefore means that the moment of inertia is, as shown there, 47 times 0.74 squared is 25.73 kilograms per meters squared. And then therefore to find the angular momentum, you would then do that times the angular velocity, which is 6 radians, so therefore the angular momentum is 154.38 kilograms per meter squared radians. And then lastly, the gymnastics turning effect, or torque. In this example here of the gymnast on the rings holding themselves up, the moment arm is the red line shown, which is 0.9 meters, and the force, as the blue arrow facing down, is their body weight, which is about 70 newtons. So then therefore, using the torque equation of torque equals force times moment arm, the torque is 63 newton meters, which means in this example the athlete is having to generate a much larger force than they possibly could have if they manipulate their body position to require less force, which they could do is if they bended their knees, which therefore would make the effort arm shorter. As shown by the blue arrow there, which would then make the force required less at this 90 degree. As shown at the bottom there with that equation, 0.54 meters would then be the moment arm with still the 70 newtons, and therefore the torque would only be 31.5 newton meters, which would therefore make it easier for the athlete to then be able to perform that movement using less force by manipulating their body position.